Drew, are we on? Okay. You ready, Jeff? Good evening. My name is Professor James LaRoche, and on behalf of the University of Louisville's Department of Physics and Astronomy, I would like to welcome you all to the second annual Andrew Chamblin lecture here in the Gain Science Hall and Rao Planetarium. The department inaugurated this lecture series to celebrate and honor the life of Professor H. Andrew Chamblin, who was assistant professor of physics at the University of Louisville until his untimely passing in 2006. Before coming to Louisville, Andrew did his graduate work with Roger Penrose at Oxford, and then with Gary Gibbons and Stephen Hawking at Cambridge. It is in his memory that the department has chosen to present to the university and to the greater Louisville community at large this lecture series with talks in the fields of cosmology, gravitation, string theory, and particle physics, areas which reflect Andrew's life work. This year we are very honored to have with us Professor Paul Wesson from the University of Waterloo in Ontario, Canada, who will present tonight his talk entitled Weaving the Universe. There's articles, I think 250 at last count, and 10 books, including Brave New Universe, Illuminating the Darkest Secrets of the Cosmos, Space, Time, Matter, Modern High-Dimensional Cosmology, and the forthcoming Weaving the Universe. A graduate of the University of London and Cambridge, Dr. Wesson has pursued research in both geophysics and astrophysics. He has recently been working on understanding the cosmological background radiation fields and the origin of mass in the universe. Tonight, he will talk about how our views of cosmology may be affected by our collective experience and how this influences our efforts to understand the laws of nature. Thank you. Dr. Wesson.
Thank you. It's my first time in Louisville, but I did in fact know about your fine city before I came here because you've got a thing called the Louisville Slugger. And although Canada is not well known in that field, we've got one good team in Toronto, which is right now doing fairly well. But if like last year, they'll soon tank. However, the main game in Canada is hockey, ice hockey. And everybody in Canada knows about hockey. And the reason why I know about the Louisville Slugger is because your company that makes baseball bats also makes hockey sticks. So throughout Canada you are famous for the origin of the hockey stick, also called the Louisville Slugger. So I don't feel like a total stranger here with that kind of background. Of course, we have to play hockey in Canada. It's impractical for us to play baseball, at least in Toronto, because nobody can find the ball in the snow. And if it goes out of bounds, then you might get dumped on by a grizzly bear. And you can't hear the umpire's calls anyhow because of the wailing of the wolves in the forests. This tends to be the image that people have of Canada. It's not all like that. And tonight what I would like to do is to try and tell you about some of the research that I've been doing in cosmology. My main base is the University of Waterloo, which is in Ontario, about an hour's drive from Toronto. However, for the last year or so, I've been on leave at the Hertzberg Institute for Astrophysics, which is in Victoria, British Columbia, right on the west coast. And what I'll tell you about tonight is basically a compilation of research which I've been doing with people at both Waterloo and in Victoria. So I'd like to start with a picture that shows two people, one of whom at least you should recognize. And he's talking to another one who will be, in fact, the main feature of tonight's talk, but who may not be all that familiar to you. Albert Einstein was the inventor of the theory of relativity, both its special and general forms. The special theory came out in around 1905 and dealt with the velocities of particles traveling by each other. The general theory came out a lot later, and some historical people in physics say, oh, why did it take Einstein so long to come up with the general theory when he already had the special theory? The answer is, it's damn difficult. The general theory is a theory of gravitation, that is, the forces on particles. It's far more complicated than the special theory. And it doesn't surprise me at all that it took him 10 to 15 years to come up with the right equations. At this time, of which we're discussing in the years, say, 1915 to 1920, there weren't many physicists doing this kind of work. And one of the few that really understood what was going on was the other gentleman in this picture, Arthur Eddington. Sir Arthur Eddington was the Plumian Professor of Astronomy at Cambridge University at this time. And they're sitting here on a bench, apparently having a chat. We can maybe speculate that they're talking about the general theory of relativity. At that time, there weren't many people in the world that even knew what relativity was, let alone the general form. Eddington was a very straight academic guy. He was dedicated to his work. But nevertheless, he had the gift of the occasional good comment that was reported in newspapers. So at about this time, when the theory was getting going, a reporter approached Eddington and said to him, "Is it true, Mr. Eddington, that there are only 3 people in the world that understand general relativity?" To which Eddington replied, "Oh yes, and who, pray, is the 3rd person?" Eddington, we see here, was not only a very clever guy, he was also the one who translated Einstein's works from German into English. Without him, probably the theory would have got a stillbirth in the English-speaking world. I'm going to try and leave, by the way, a good time at the end of this lecture for people to ask questions. So please let me just carry on, and then if you have questions, I'd be very happy to answer them at the end. Most of what I'm going to talk about is Eddington's view of the world. I'm not going to go into great detail about his views concerning gravitation or general relativity or his relationship to Einstein, because what Eddington is now mainly remembered for is not so much his mathematical work as his philosophical work. In his later years, he branched out into writing philosophy. What he tried to find out was something that may sound quite simple, but is in fact very profound. What he wanted to know is, the science we do, where does it come from? Where do the equations that we write down, and which all of you can read in textbooks, what's their actual origin? The majority opinion at the time was that, of course, that you discover these things. You do it by experiment and theory, usually with experiment leading the way. Traditionally, you would do an experiment, and then you would follow it up with some theory. Or if you did it the other way around, the theory was never far away from the experiment, time-wise. Eddington thought about these things for a long time, and he came up with a different viewpoint. And it is